Okay, so at this point, I think the best thing to do is to try to run PCA in R and get the outputs and have a talk about them one at a time. So I'm going to start with this ERIS dataset. You can download it from a lot of places because it's a dataset that's used a lot in coding examples. So I'm going to call it ERIS, and I'm going to read it as a CSV file. So I'm going to run this line. Okay, so here's I have 150 observations, and I have 4 variables and another factor, which are the different species names. Now, I want to give them names that are more meaningful, so I'm going to use col names and just give a vector of column names. So it's not V1, V2. I'm going to give them names so I know which one is which. You don't have to do it, it just makes it prettier. And if I use the command pairs, I can plot all the combinations, okay, like we spoke about earlier. You know, if you stretch this window, you can see it better. So we saw this in the lecture. You know, here the length and width are actually quite highly correlated. Okay. The next thing I need to do is test normality and things like that before I enter PCA. I'm not going to do that right now. Some of the data is not normal, and I'm going to fix that by log transforming it. But for now, I'm just going to focus on this. So this is to do with the checking for normality, logging in, checking for normality again. But I'm going to look at this part here, which is actually doing the PCA. So I'm going to generate this matrix, which is the IR PCA. That's what I called it ERIS PCA. And I use prcomp is the command for PCA. On which dataset? On this ERIS dataset. Now, IR is a shortened version of the dataset because the first column, well, the 5th column is species. It's not one of my variables. Remember, we have 4 things that we measured. So I'm actually going to carve that one out and going to put it aside as IR. And it's only columns 1 through 4. So I've only kept the measurements. And that's what I'm running a PCA on, not on the names. So I am going to run it. I need to center it, and I need to scale it. Remember, we said that, which is why these two have true. And that's it. That's all I need to do. I'm going to run this. Oh, I haven't defined it. Let me just do this. And here's my PCA right now. It has the rotations, all sorts of rotations. It has the center and the scaling. And it's here are PC1, PC2, PC3, PC4. We're going to have a look at it closer up. Okay, so I'm going to print this. Okay, so here are the rotations of the matrix. So PC1 has, we do something to sepal length, to sepal width, to petal length and petal width, and then PC2 and PC3 and PC4 are all orthonormal to PC1, right, at 90 degrees. And I can actually plot this. And this is called a scree plot. A scree plot tells me how much of the variance is explained by each principal component. So principal component 1 is explaining a lot, 2 adding a bit more, 3 and 4 no longer necessary. So if I want to know how much this is in percentages, I can print, of course, the summary of these different principal components. So it tells me the proportion of the variance that is explained by principal component 1. That is very high. 73% of the variance is explained by PC1. When I look at, oh, hold on, I'll show you in a minute. When I look at PC2, it's explaining 22%, but together they're already explaining 95% of the variation in the data. So PC3 and PC4 are no longer adding a lot. I can really simplify my model by reducing the dimensionality using PCA to get only PC1 and PC2 to matter. Now I can run this scree plot again. And here you see it here, but I see that 1, 2, 3, 4. Okay, so 1 and 2 together are still explaining. 1 is really doing most of the heavy lifting. But I'm interested to know, but who is 1? I mean, like, so I've measured these 4 parameters. What you're really telling me is that I can generate, from these 4 things, I can generate these axes, just 1 and 2, that will give me a good, will capture the variance in the data very well. So what is PC1 made of? What is PC2 made of? I can look here using a biplot. And this is using, oh wait, I need to call IR species as well. I have my points labeled as the species, so we have species 1, 2, and 3. And then I have, this is called the biplot. It has PC1 and PC2 and the eigenvectors. So when I think about, oh, what is PC1 made of? It's made up of petal length and width, but can you see how high this redundancy is? So PC1 basically got rid of this redundancy. And then I have a little bit of sepal length. Okay, it has a component in here. So if you imagine this is, and we're thinking about here, I'm going to show you something I have here. So here's a loading plot. Okay, so here are my new PCs, PC1 and PC2, F1 and F2. And here is my original variable. Okay, and now it has a loading A1 that is the dot product really of how much of V, the original V, is placed in F1. Okay, and that's called a loading. And then I have how much of the V is actually falling onto A2, right? So these are called loadings of the eigenvector elements. Okay, so that's what you're seeing here. So we're seeing that the loadings are very high for these two, but really I don't need two. They're saying the same things. These vectors are pointing in the same direction. There's very high correlation here. There's very little correlation between petal length and sepal or sepal width, right? So there's this one's giving me a lot of new information. It's kind of, this is the heavy lifter for PC2. And if I come back to R and look at the principal components, I can see that principal component 2, indeed, the heavy lifter is here. This is causing the greatest rotation for PC2, and that's the width. Okay, that's why it's so high over here. So what else can I show you here? Okay, so now we want to know what those loadings are. And the loadings are really taking the correlation back between the different PCs, the principal components, and the original variables. So if I can do that for you, you'll see these length and width have really high correlations with PC1. So does the length of the sepal. And so the petals are very much to do with PC1. And here we have a high correlation with the width, okay? And then PC3 and PC4, we have low correlation with all of those things. They really don't explain much of the data. So this is looking at the eigenvector. Oh, sorry. What do I need to do? IRPC. I think I'm supposed to have something here that I didn't fill out. Okay. That was it to show you on the computer and to show you the different loadings. Okay, so the loadings are really just, I just wanted this plot from here. We'll come back to here. So we have these, so obviously there are very high loadings between oxygen and temperature in PC1. So that was the, okay, coming back to the normality. So we've measured normality using QQ plots or in previous computer labs. But when you test for normality on a multivariate data set, so you have multiple variables, you need to do some sort of bivariate normal distribution. There are a few ways to do this. I give an example code, but really it works like a chi-square of QQ plots. It has all sorts of distances to a centroid, and here we see it should fall pretty much on the line. We can see that things are not falling on the line well, which is why we logged it. So in practice, it is actually quite simple to solve a PCA. I'm sure if you go back to the code, and the code is on Moodle, you can work it out. But the mathematics behind it are actually quite complex. But now you understand that you have matrices and vectors that rotate these matrices. And the bigger the loading of each, the importance really of the different original vectors to the loading tells us how important each original variable is to the rotation of the PC1 and PC2. So I have here the loadings that indicate the weight of original measurements on the PCA. Okay, so here is that information you just saw. You have, it's also called influence scores sometimes. And the array of these loadings together are the eigenvector, because each loading is for one of those bases, one of those cameras, if you will. And together we have an eigenvector that's moving it in the multidimensional space. So A1, A2, all these different loadings are elements of vector A, okay, the eigenvector. And then when we have A times X, the matrix, the variance is maximal when all of these equal 1, okay? And then we looked at scree plot, which is another way of looking at how the variances are associated with each principal component. And we're looking for a drop. So we're looking for where this is tailing off, okay? So I can see that actually after 2, I'm pretty much done. The fourth component, because remember we're going to have as many components as original variables, but the fourth and the third component, I don't need them to explain variance. So how much variance is captured by this axis, I can see in the summary as well of the PCA output. So here's the standard deviation, and I can see that it's high in PC1, high in PC2, getting lower and lower, and the proportion, a cumulative proportion, is here. And by the time I get to PC4, I should have all of it. Okay, so I can scale these vectors to represent the loading as well. I mean, like so. There's a strong. These vectors have a certain length, and that length is the loading on each of those axes. Remember, each one of those has a loading on PC1, and a loading on PC2, and a loading on PC3, and a loading on PC4. So what can I see here? I can see that these two are highly correlated. And I can see that variability across 3 species is accounted mainly by PC1. I can see PC1 explains a large part of variability in sepal length as well. I can use PC1 and PC2 a little bit as response variables for testing response to environmental variables, etc. So PC1 is now, it's a thing. I can use PC1 instead of measuring those 4. I can just run my analysis on PC1 and PC2. So I can use PC1 to identify species. I still need to make those 4 measurements, right? So here are the correlation matrix between the original variables and the principal components. So when I think about it, I need to have, there's a high correlation between PC1 and all of these. Sepal width, a little bit less so. Remember, it was mainly driven by PC2. Okay, so here you can have these are PR comp, okay, the one we used, and these are the inputs it takes. So we need to center, that's the variable means that we subtract, we scaled, and these are the things that went in